Over recent years, SCI has experienced a steady increase in demand for its thermal modeling services of construction details in fire, while more recently, a thermal modeling methodology to assess thermal transmittance and condensation risk has also been developed. Both of these services, which include thermal modeling and assessment of construction details, are offered as a new all-around in-house SCI consultancy service. Now, why should SCI develop this service, and is there a need for it? The most obvious reason is that with a focus on net zero carbon solutions, as we see from the unfolding events in COP26, the thermal performance design of buildings is of more interest than ever before to be as energy efficient as possible. An efficient building is one that requires minimal energy to warm or cool down. The second reason relates to fire design, and although it has always been in the agenda, after the Grenfell Tower events, there is more interest and scrutiny in fire design. New policies and regulations are demanding stricter design for fire accidental scenarios. The third reason for why the thermal modeling is needed and not simple calculations are adequate for determining the thermal performance characteristic is simply because buildings nowadays are built much more complex. They are not made up of just one or two materials like brick and mortar. Walls and floors, which make up the building envelope, are multi-layered with different materials and systems in place, as shown by the wall example from Kingspan. The SCI is in a unique position to help the industry in providing consultancy and assessment of construction detail solutions for the building envelope towards a more efficient insulation system, contributing to the net zero carbon philosophy. So when we refer to the term building envelope, what we specifically refer to is the walls, floor, roof, windows, and doors. It is the physical separation between the interior and exterior. That is the climatic modifier that creates and contains the internal conditions. SCI has been involved in several multi-year and multi-partner projects with focus in the thermal performance of buildings. Two of these projects where SCI has acted as the coordinator partner were Tabasco and Batimas. Among other topics, the importance of thermal bridging in steel construction was investigated for both hot-rolled steel and light steel frame systems. Thermal bridges within the thermal insulated layer of a building or at junctions in building envelopes occur in all forms of construction and should be minimized as they add to the overall heat loss. For structures in steel, since steel has high thermal conductivity, this is of great importance. Thermal bridges occur where the insulation layer within the building envelope is penetrated by material with a relatively high thermal conductivity and interfaces between building elements where there's a discontinuity in the insulation. Thermal bridges result in local heat losses, which means that more energy is required to maintain the internal temperature of the building. Lower internal surface temperatures around the thermal bridge, which can cause condensation that may lead to mold growth. SCI's most recent publications on thermal bridging and guidance to minimize their effects are P410, which focuses on structures with hot-rolled steel members, and P411 for light steel framing and modular construction. While P424 is one of the latest SCI publications, and as Callum touched upon, it provides guidance on how light steel frame buildings should be designed and detailed to provide fire resistance in accordance with the building regulations. To assess an element in fire or thermal insulation, certain design criteria need to be determined. For fire, this is the resultant temperature profile of the system in consideration after a 30, 60, 90, or 120-minute exposure to fire. While the thermal insulation performance of a planar element can be expressed as a U value, which relates to an area, or a psi value, which is associated with linear thermal transmittance. Condensation risk, given by the calculation of FRSA value, may be determined accurately using advanced thermal modeling, but more details on this a bit later on. An assessment will allow to quantify the effect of thermal breaches and the consequence on the use of appropriate thermal breaks to minimize heat loss. SCI has developed algorithms for facilitating the conversion of 2D CAD construction details into 2D or 3D thermal models for use with software such as the finite element analysis software, which is capable of carrying out a transient heat flow analysis, allowing to study a fire case scenario where the radiative heat transfer is nonlinear. For a thermal analysis where the insulation properties of a construction detail are needed, such as thermal transmittance or the risk of condensation, the Trisco software is preferred, which allows detailed 3D modeling in a steady state heat flow analysis. Therefore, a thermal insulation model analysis is a static flow one, with the relevant boundary conditions defined on the external and internal surfaces with the respective temperature transmittance conditions. In the fire model, a heat source is modeled with the temperature varying in time. The Eurocode standard time temperature curve described in Eurocode 1, Part 2 was used for the application of convective loads. In a fire analysis, once the temperature data are obtained, the structural performance of the components can be determined at elevated temperatures. For steel components above 400 degrees, the strength is determined using strength reduction factors from Eurocode 3, Part 1, Part 2, and a similar procedure can be applied to other structural materials. The finite element models can include components of various different materials which need to be modeled accurately in the software. Thermal properties of the materials, such as thermal conductivity and specific heat capacity, need to be specified. For many materials, these properties vary with temperature, although for steel, these properties are given in Eurocode 3, Part 1, Part 2. For many other materials, such as plasterboard and insulation, are not readily available. Therefore, it is often necessary to calibrate finite element models against test data. This may typically be achieved using temperature data recorded during fire testing of an element construction, for example, a wall or floor, which includes the same materials in a similar arrangement to the construction detail being modeled. The graph shows how the test and FE compare for a light frame load-bearing wall case study, where the characteristics of insulation and plasterboard were parametrically studied. Another aspect to consider is that not all components will be permanent in a fire situation. For this reason, SCI has developed a methodology of thermal modeling which allows specific components of the detail to be removed from the model at a specific time. The methodology then allows the analysis to continue from the point where the element was removed with a continuation of the temperature profiles. As illustrated here, the FE model is simulating a case scenario where part of the wall is destroyed. The location of the furnace, which is the heat source, relative to the construction detail being examined needs careful consideration and skill by the modeler, as this can be significant to the results. The SCI has carried out this type of thermal analysis for fire conditions for a range of construction details, including hot-rolled hollow section columns in modular frames, light steel frame walls and junctions, composite slabs and support details, steel beams embedded in concrete, and hot-rolled steel edge beams, which is illustrated here with the graph showing how the temperature of different parts of the beam, such as the web and flanges, vary in time with increasing temperature. Now, moving from fire to thermal insulation, to satisfy the building control requirements of thermal efficiency efficiency in the UK, it is necessary to demonstrate compliance with the building regulations. Part L of the building regulations addresses energy efficiency requirements in buildings in England and Wales. Section 6 of the Scottish Building Regulations is the technical handbook that deals with energy within the built environment. Similar regulations exist for Ireland. SAP 2012 and SBM are the two national calculation methodologies for calculating the energy performance of a building. SAP 2012 is a standard assessment procedure for dwellings, and SBM is the simplified building energy model for buildings other than dwellings. Both SAP 2012 and SBM require the designer to have knowledge of the thermal bridges because heat losses through thermal bridges must be included in the calculation of predicted rates of CO2 emissions. Regulations generally use the U value as the measure of thermal insulation of planar elements because it includes the three major ways in which heat loss occurs: conduction, convection, and radiation. A lower U value means a higher level of thermal insulation. The units of a U value are watts per meter squared per degree Kelvin. Repeating thermal bridges, such as C-sections, located with the insulated layer of light steel walls or brick ties should be included in the U value of planar elements. Non-repeating thermal bridges such as floor junctions, window sills, and ridges from additional heat transfer paths that are not accounted for in the elemental U value. These are accounted for in energy performance assessments by the linear thermal transmittance Psi value for each thermal bridge. The units of the Psi value are watts per meter per degree Kelvin. The heat transfer associated with intermittent or singular elements such as beams or other elements can be quantified using the pod heat transmission coefficient He with watts per meter as a unit. Low internal surface temperatures in the region of a thermal bridge can lead to surface condensation if they are below the dew point of the air. BS 5250, Code of Practice for Control of Condensation in Buildings, describes the causes and effects of condensation in buildings and gives recommendations for their control. Further information on condensation due to thermal bridge is provided in BRE Information Paper 1-06. An indicator of condensation risk is provided by the temperature factor FRSA. This factor is given by this equation found in the BRE paper. Accurate calculation of the surface temperatures is achieved through thermal modeling. Minimum recommended values of FRSI, termed critical temperature factors, FCRSI, are presented in the table. The critical temperature factors depend upon the building use and the expected internal relative humidity of the building. The higher the likely internal humidity, the higher the critical temperature factor should be to eliminate risk of condensation. A case study scenario here compares the thermal performance of a detail with direct connection of a steel balcony to the concrete slab with one with a thermal break between the steel and the concrete slab. The calculated FRSI value with a thermal break is increased by about 30%, indicating a decrease in the risk of condensation. Other studies involve parametrically investigating the effect of changing the insulation thickness on a wall and junction as shown in the two details for light steel frame systems. With increasing insulation thickness, lower U and Psi value are observed. Thermal models can also be built in 3D when construction details require it. In this example, a light frame steel wall is connected to a solid concrete wall with the use of a wall bracket. The effects of the wall bracket acting as a bridge can be viewed in the temperature contours after the thermal analysis. Another 3D model here is a detail of a window corner with the inside wall set as 20 degrees and the outside as 0 degrees. Not only a planar member or a junction, but a section of a building or a whole building may be modeled. In this example, the influence of a penetrating steel beam and its effect in thermal performance and condensation risk is assessed. At SCI, we're adaptable with the needs of the job and the client. We can model in 2D or 3D if needed, carry out parametric and optimization analysis. The project may just be a planar element or a large section of a building. And if we cannot do it with the current tools we have now, we welcome the opportunity and challenge expanding our knowledge for the needs of a certain project. The perks of having SCI carry out thermal modeling and assessment of your product or design is ensuring compliance with the codes and building regulations. There is also our proven credibility and continuous support throughout the project's life, and not only, since for our members, support is always our priority. We have the expertise of skills, experience, and knowledge to bring value. Thank you.